Hello, welcome back to Chapter 7, Section 6, where we're talking about the base of the natural logarithm. I don't like the way they say the natural base, which is the number e. Now, in this example, we're going to talk about the natural logarithm. We've talked about the common logarithm, which is this one right here, where that's base 10. And again, that's because that's how we count. Probably. I have to say probably because every time I look it up and read about it, they say this is what we think happened. All right, we don't have evidence. You know how scientists are. But it's probably. I mean, why else would it be 10 if it wasn't for the 10 fingers? For this video, we're going to talk about a logarithm with base e. And the way that we write that is not this. We actually write this. No. Yes. Why? Because the base is something that, like I said, if it wasn't for humans, math would probably be in base e. It occurs naturally. It shows up in some really, really wonderful places, like that interest problem that I did in the first video. The LN actually stands for Logarithm Naturel, which is French. And yeah, you pronounce the L at the end of naturel. Okay. I don't think you pronounce the M though. Okay, Logarithm Naturel. It always bugged me about French, why you only pronounce C, R, F, and L at the end of words. And I'm sorry, I'm not going to take it up with Mr. Curry. Okay. But one thing about French, which for many years was the language of mathematics. One thing about French is that they like to put their adjectives after the nouns. Okay. So instead of the brown cow, the cow brown. Okay. Maybe. I don't know. I had trouble with French because I don't know why tables are female. I don't know. Anyway, so that's where it comes from. A lot of the communications that have happened like the last couple of 100 years have occurred when mathematicians would talk to each other. They picked a language so they could communicate, and that language was French. So, for example, Sir Isaac Newton, who was English, the chair of the Oxford Astronomy Department, or whatever that is, his famous book where he invented calculus was written in French. So anyway, but you don't need me to talk about this in this video. That's just why we do LN and not NL. Okay. So that's why common logarithm, but we also have this logarithm. These are the two important logarithms that you're going to see, which is why we put them on the front of a scientific calculator. Okay. So, but basically these are the same, just the way that we write it. Now, in this example, in this video, we're going to be talking about, properties. And these are the properties that we learned back in 7.4, and the B just stands for whatever base that you want. Okay? So base 2, base 7, base 10 with common logarithm, because these properties work for every logarithm with any base. That means that they also work for the natural logarithm with the base e. So I can rewrite all of these like this. So the product property, I'm just going to abbreviate, natural logarithm of m plus the natural logarithm of n equals the natural logarithm of whatever m times n is. That is that, except I'm using e as my base. The quotient property, the natural logarithm of a number, and m and n are just numbers, okay? Just like they were up here, they're just numbers. Plus the natural logarithm of another number, well, darn it, excuse me, subtract. I got ahead of myself. If I'm subtracting the logarithms, this is the natural logarithm of the quotient of those numbers, just like this one. The power property works. So if I take the natural logarithm of some number raised to some power, that's the same as that number times the natural logarithm of a. That power times that natural logarithm of a. And I can show you that one real quick on the calculator. So if I do natural logarithm, I'll do, say, 3 to the second power. Okay? Whoops. Delete. Forgot I gotta get out of my... Now, so that's going to be about 2.19. Okay? In other words, this means e to the 2.19 power equals 9, 3 squared. But if I do this, 2 times natural logarithm of 3, I get the same thing. So that's an example of the power property. And of course the inverse properties, because everything is dependent upon the base, the natural logarithm of e to the x power just equals x, and e to the natural logarithm of x equals x. Okay, so let's do some simplifying. Now, again, I cut and paste these from the book, and they are doing something with the logarithms that I've mentioned many times that I do not like to do, or that I wish they wouldn't do. I have to put parentheses around this. That they put the parentheses in there, okay? Okay. This is going to be the inverse property. The natural logarithm of e. Remember, natural logarithm means log base e. We just don't write it that way. That's going to be hard to remember, so write that down someplace. If the logarithm, the base of the logarithm, is the same as the base of the exponent in here, this is saying, what's the exponent on e if I have e to this exponent? Well, duh, it's just the exponent. So this is saying, e to what power equals e to the negative 2t power? That's just straight up negative 2t. I don't know what t is. I don't know what the value of t is. Does not matter. But I know that if I take the natural logarithm of e to any power, it's just going to be that power. And the reverse is true. If the exponent on e is a natural logarithm, then these are inverses of each other again. So e to the power of a natural logarithm, I don't know what t minus 1 is, it doesn't matter. This equals t subtract 1. They just undo each other, all right? Same thing with this one. This looks just like that. This is 3.2. And this one, because I'm not using a t, I can actually do this. Natural logarithm of e to the 3.2 power, wait for it, just 3.2, it's just the exponent. Same thing with this one. This is just x plus 4y. Now take a gander over those 4. They're not hard. It's just straight up saying, have you been following along? The only purpose of these is to say you learned the properties with logarithms back in 7.4. All these properties are still true, even though it's a natural logarithm, and it just looks different, but it's still true. Remember, natural logarithm of x means log base e of x. We just don't write it that way. We write it this way, right? After saying all that, let's look at the last two that I have here. You're going to be tempted to just say, oh, this is just x. But think about this. This is 5 times natural logarithm of x. This is 2 times natural logarithm of x. That 5 and that 2 have something to do with it. What if I covered up the e and just, it's still there. I didn't make it disappear. Okay, please don't assume I'm just saying, hey, let's just ignore it. I'm just saying, like, let's just look at this one part real quick. When I have a number multiplied by a logarithm, That's the power property. Here it is in, well, actually, let's look at this one. Here it is with natural logarithms. So this is 5 times natural logarithm of x. So that would be like 5 times natural logarithm of x. So what I got to do? I got to put that exponent back where it was. So this is e to the power of the exponent, natural logarithm of x to the 5th power. Now I can use my inverse property and say x to the 5th power. For this one, this is e to the natural logarithm of x to the 2nd power, and of course that just equals x squared. So they're sneaking in the power property in here. So we got that going on. Okay, that's all I'm going to do for that video. We'll see you in the next one.